Welcome to a screencast on the rest of the material from class that we started on Wednesday, February 15th. Or if you prefer, you could think of this as the material we would have done on Monday, February 20th if we didn't have a holiday that day. And you can take notes on the rest of the handout from Wednesday the 15th. This is the stuff that was on there that we're going to be covering. Okay, first of all, we started this one in class. This is classifying solutions of salts as acidic, basic, or neutral. And if appropriate, write the appropriate hydrolysis reaction. Well, first of all, KCl is an aqueous salt or salt in aqueous solution. It dissociates into the K plus ion and the Cl minus ion. We look at each ion separately to see if it has an acidic or basic character or if it's just neutral. And K plus has no acid-base effect. Positive ions typically, if they have a small charge, have no acid-base effect. And we'll talk a little more about that in a bit. Cl minus, like other negative ions, could possibly be a base, but Cl minus is the conjugate base of HCl. And HCl is a very strong acid, and in fact, it's so strong it fully dissociates. Therefore, Cl minus is such a weak base that it has essentially no basic effect. And so we have no acid-base effect from the K+, no acid-base effect from the Cl minus, and so this is a neutral salt and no hydrolysis equation. NaHCO3, sodium bicarbonate, is an ionic compound that in aqueous solution dissociates into the sodium ion and the bicarbonate ion HCO3 minus. As we saw previously, Na plus has no acid-base effect, too small a charge. HCO3 minus could potentially function as a base because it's the conjugate base of H2CO3, carbonic acid. And carbonic acid is a weak acid. Therefore, its conjugate base, even though it's also a weak base, it's not completely weak like Cl minus is. And since it is a not completely weak base, it has some basic effect. And so we have a basic solution because one of the ions has no effect on acid or base. The other ion has a basic effect. So overall, this solution is basic. Now, the hydrolysis equation is going to come from the ion that has an effect on the acidic or basic nature of the solution. And hydrolysis means breaking apart of water. And a bicarbonate ion is a conjugate base of a weak acid. Therefore, at least partially, what it can do with water is gain a hydrogen from the water, making the carbonic acid and splitting the water into an H plus that adds on to the HCO3 minus to make H2CO3, and then OH minus makes our solution basic. So that is the hydrolysis reaction showing the basic character of this solution, which is due to the bicarbonate ion, and due to the bicarbonate ion being a weak base conjugate of the acid H2CO3. Next salt is NH4 NO3, ammonium nitrate. This dissociates in aqueous solution into the ammonium ion NH4 plus and the nitrate ion NO3 minus. The nitrate ion, let's do that one first, is the conjugate base of the strong acid HNO3, and just like we saw with the strong acid HCl, this has a conjugate base that's so weak it has no acid-base effect. On the other hand, NH4 plus is the conjugate acid of NH3. And NH3 is a weak base, but it's not completely weak like NO3 minus. And so the conjugate acid of a weak base has an acidic effect. This only has a +1 charge, but NH3 is a base. NH4 plus is its conjugate acid. This is different in terms of size of charge from the Na plus that we dealt with previously, where we were just simply dealing with an alkali metal ion as opposed to a molecular substance that could have been a base, and in this case, conjugate acid of the base NH3. So this is an acidic salt because of the NH4 plus being a weak acid, and the hydrolysis reaction for this comes from the NH4 plus, and if we have water around with an NH4 plus, then what ends up happening is the NH4 plus can donate a proton to the H2O, produces NH3, the conjugate base of NH4 plus, and H3O plus, and that is the H3O plus makes it an acidic solution. So that's the reaction showing the acidic nature of this solution. Okay, and the last salt to do is Fe NO3 or iron 3 nitrate. In aqueous solution, this dissociates into the iron 3 plus ion, Fe3 plus, and the nitrate ion. I'm not trying to balance things here, just noting what the two substances are. As we saw previously, NO3 minus, weak, very weak base, conjugate of the strong acid HNO3, so no acid-base effect. But Fe3 plus has some acidic effect because it is a positive ion with a big enough charge to hydrolyze water. So here's how this works. In aqueous solution, positive ions end up getting surrounded by water molecules. Negative ions do as well. The stronger or bigger the positive charge, typically the more water is able to associate with or attach to that ion. Previously, we saw a sodium ion with a +1 charge, and that is not a big enough charge to have the effect that's about to be described. But +2 ions, +3 ions, especially if they're small, so typically we say small, highly charged, hydrated ions, end up having an acidic effect on solution. So if we have an ionic compound that contains a +2 or +3 charged ion, especially if it's kind of small, we expect this to have an acidic effect on the solution. Iron ends up having 6 water molecules bound to it, so it's a FeH2O6 with an overall 3+ charge because iron's 3+ and water is neutral. And this complex ion makes the salt, or the solution of the salt, acidic. And the hydrolysis equation, if this is acidic, what ends up happening is this FeH2O6 3+ in the presence of water ends up from this FeH2O6 3+, it donates a hydrogen to the H2O, donates a hydrogen ion to the H2O, makes H3O+, and that hydrogen ion comes from one of the 6 waters. So 5 waters are left intact, and then the 6th water is not an H2O, but it's just an OH, and the charge goes down from +3 to +2. It goes down by 1. And this is the hydrolysis reaction for the reason that the solution containing Fe3+ is acidic. Now, it probably would help to look at what's going on a molecular level here. So here is an image of an Fe3+ surrounded by 6 water molecules, and then there's some water nearby from the solution. And iron 3+, being a highly positively charged ion, pulls electron density towards itself from all of these waters. And what ends up happening is, since electron density is essentially a bond, electron density holds the Fe to the H2O, electron density, shared electrons, holds bonds the O to the H in each of these water molecules. And if enough electron density is pulled towards this positively charged central ion, we could say that it weakens a bond a little bit between the O and the H, and at any given instant, in a given FeH2O6 3+ hydrate or ion, one of the water molecules might have its bond weakened enough for an H+ to break off and attach to an H2O. So we have Fe3 plus in the middle, 1, 2, 3, 4, 5 water molecules intact. The sixth water molecule loses an H plus, and so the molecule that's left, or the complex ion that's left, is FeH2O5 OH2 plus, and it produces H3O plus, which makes the solution acidic. So that's what happens in solutions that contain a small, highly charged positive ion. Now we can use this kind of reasoning, what we just did previously, looking at the structure of the hexaaqua iron 3 ion, and using that to explain why it behaves as an acid in aqueous solution. We can apply similar reasoning to look at structures of molecules and use that to determine or compare acids in terms of how strong or how weak they are. So this is a group of three somewhat similar acids, very similar in fact: HOCl, hypochlorous acid, HOBr, hypobromous acid, and HOI, hypoiodous acid. They all are H bonded to O, bonded to a halogen molecule. But the halogen molecule differs: Cl in one, Br in another, and I in the third. So differences in structure would lead perhaps to differences in strength, and in this case the only thing that's different is that terminal atom, the Cl versus the Br versus the I. So things that can differ are Cl is a smaller atom than Br, and Br is a smaller atom than I. So size of atom might make a difference. And the other thing is Cl is more electronegative than Br, and Br is more electronegative than I. And typically both of those factors could be things we'd consider in terms of affecting the properties of the substance we're looking at. And it turns out in this case it's the electronegativity or electronegativity difference that's the bigger factor. So HOCl, here we're showing Lewis dot structures, HOBr and HOI, and what makes each of these acidic is that the bond between the H and the O can break, and an H plus can dissociate from this molecule. Now, as we saw previously, if the electron density between two atoms is not as much, then that bond can break more easily, the substance can dissociate more easily, and so we should be looking at the relative strength of these bonds, or how much electron density we have. And the key factor is, since Cl is more electronegative than Br, and Br is more electronegative than I, Cl is going to withdraw more electron density towards it than Br will, and Br will do the same, will withdraw more electron density towards it than I. And withdrawing electron density from a little farther location in the molecule ends up getting a weaker bond. Withdrawing less electron density makes a stronger bond. So we'll actually start with a known K sub A value for hypoiodous acid. It's a quite weak acid. K sub A is 2.3 times 10 to the minus 11th. And we would expect now, by comparison, HOBr, hypobromous acid, to be a little stronger, because Br has a higher electronegativity than I, withdraws more electron density, weakens this HO bond a little bit more than the HO bond in HOI, and so we'd predict a somewhat larger K sub A value, and it turns out it's 2.8 times 10 to the minus 9th. And then for HOCl, same essential idea. Cl is more electronegative, withdraws more electron density than Br or I, gets a somewhat stronger acid, somewhat larger K sub A, and 2.9 times 10 to the minus 8th for HOCl. Now, there are other things that we can deal with in terms of molecular structure affecting acid strength, but this is one of the biggest factors, and so that's an example of that. So here's our answer: strongest acid HOCl, weakest acid HOI, due to electronegativity differences between the terminal atom. Otherwise, these molecules are the same. Okay, so now let's try this kind of analysis, but rather than for comparing some acids, let's compare some bases. The structures for aniline on the left and 4-chloroaniline on the right are shown here. We have a benzene ring, 6 carbons in a hexagonal ring in both cases. We have an NH2 in both cases. That makes it a base. There's a lone pair here that can accept a hydrogen ion. Same thing here. And then the difference is 4-chloroaniline has a chlorine opposite where the base group is, and aniline does not. Now, there's a couple different ways you can look at this, but I actually think it's easiest to think of this or to look at it in terms of conjugate acids and comparing them. So there's NH2 in each case, the base form. And if we imagined forming the conjugate acid, in each case we'd add an H+, and H+ would be added on here, H+ would be added on there. These are the conjugate acids of those respective bases. And now if we look at how strong the conjugate acids are, we're looking at how easily an H+ dissociates from this molecule. And this molecule has a chlorine on it, the 4-chloroaniline. And chlorine, as we saw before in the previous example, is quite electronegative. It withdraws electron density from as far away as this in the molecule. And if it withdraws electron density from the N to H bond, or one of the N to H bonds out here, more than is happening in the molecule aniline that doesn't have chlorine on it, it's going to weaken the NH bond in the 4-chloroaniline more than the bond in the aniline, and that would make this the stronger acid. And of course, the stronger acid has the weaker conjugate base. So if we look up the case of B value for aniline and we get that it's 4.3 times 10 to the minus 10th, we could predict that 4-chloroaniline would have a smaller case of B because it's a weaker base corresponding to the stronger conjugate acid. And it turns out that that's true. We get case of B is 1.4 times 10 to the minus 10th, less than 4.3 times 10 to the minus 10th. Okay, the last thing we'll do is to look at, or at least last thing on this screencast, is to look at what are called polyprotic acids. H2SO4 is sulfuric acid. Here's a ball and stick molecule representation of H2SO4. And so there's a hydrogen bonded to a sulfate ion. H2CO3 is carbonic acid. Here's the structure shown for that. H3PO4 is phosphoric acid. Here is a space-filling molecule or molecular image of phosphoric acid. 1, 2, 3 hydrogens. We call acids like this polyprotic acids, meaning poly or many protons or hydrogen ions can dissociate from these acids. So carbonic acid, for example, can have this hydrogen ion and that hydrogen ion dissociate. Sulfuric, this one and that one, and phosphoric, all three of these. Hydrogen ions can actually, or hydrogens can actually dissociate from the molecule. Well, when we deal with monoprotic acids, they have a case of A, or acid dissociation constant value. When we deal with polyprotic acids, they're going to have more than one case of A value. So they have a case of A1, a case of A2, possibly even a case of A3. So carbonic acid, oxalic acid, sulfuric, and sulfurous are diprotic acids. They have two hydrogens that can dissociate. Phosphoric acid is a triprotic acid. It has 3 protons that can dissociate, and so it has 3 case of A values. Like other case of A's for monoprotic acids, these can be found in tables, and they can be determined experimentally. So, how do we deal with calculations involving polyprotic acids? And we'll do one example here, that is calculating the pH of the polyprotic acid, the diprotic acid, H2SO4 or sulfuric acid. Well, back in Chem 1A, we would have thought of H2SO4 as simply a strong diprotic acid that has two hydrogen ions that can dissociate. When they do, they make two hydronium ions, and so we might have looked at the acid dissociation of sulfuric acid, something like that. Now, it turns out that sulfuric acid, we call it a strong acid, but it's really only the first, so to speak, dissociation of hydrogen that is a complete dissociation. The second hydrogen ion does not completely, or second hydrogen on molecule, does not completely dissociate. It has a K sub A value that's fairly big for K sub A's, but it's not very large, it's not complete. So what ends up happening is H2SO4 dissociates fully to make HSO4 minus and a hydronium ion, but then that HSO4 minus only partially dissociates, so we have an equilibrium here that's not completely product favored for the second dissociation, and we don't completely produce the SO4 2 minus or sulfate ion. Now, how do we calculate with this? Well, the general process with diprotic acids, or for that matter triprotic acids, is to just do things stepwise. Treat one dissociation, then after that's done, treat the second dissociation. So the first reaction or first dissociation is H2SO4 with water makes H3O plus HSO4 minus. If we set up our usual ice table, our nominally initial concentration is the 0.1 molar. We ignore the water and we'll pretend it hasn't dissociated. Then the change will be that the H2SO4 goes down and the H3O plus and the HSO4 minus go up, so minus X plus X and plus X. And then at equilibrium, the first equilibrium, we have 0.1 minus X and then X and X. Now, in many cases, we'd have a K sub A value and we'd set up our K sub A expression, H3O plus times HSO4 minus over H2SO4, and that ratio will equal some value. And then we'll have to do an equation solving for X. Well, in this case, K sub A1 is very large, too big to even really be measured. And what that means is we have complete dissociation. The products, so to speak, are very big. The reactants are essentially zero. And so what we end up having is X is really just the 0.1 molar. It fully dissociates. So H3O plus at the first equilibrium is 0.1 molar. HSO4 minus is also 0.1 molar. And H2SO4 is 0. Okay, now in a case where the first dissociation is not complete, we would get different numbers, but this would be the general process. Okay, now we're going to remember these. We know that H3O plus is 0.1 molar after the first dissociation. We know HSO4 minus is 0.1 molar after the first dissociation, and H2SO4 is 0 molar after the first dissociation. And then we move on to the second dissociation. And the second reaction, the second dissociation, is HSO4 minus plus H2O makes H3O plus SO4 2 minus. This is going to have double arrow equilibrium because it's only going to be a partial dissociation. And our initial for the second dissociation is going to be the final from the first dissociation. We pick up where we left off, in other words. And we saw in the previous calculation that we ended up with 0.1 molar HSO4 minus, so that's our starting point for this. And unlike in previous monoprotic acid calculations, the initial H3O plus is not 0. In this case, we ended up with 0.1 molar H3O plus at the end of the first dissociation, so that's our starting amount for the second dissociation. And then we are treating this as if it hasn't dissociated the second time yet, so our starting amount of SO4 2 minus is 0, and then because the SO4 2 minus concentration is 0, the reaction has to go to the right, so minus X plus X and plus X. And at the second equilibrium, at the end of the second dissociation, HSO4 minus is 0.1 minus X, H3O plus is 0.1 plus X, and SO4 2- is X. So now we use our second dissociation equilibrium constant, Ka2, which is H3O plus times SO4 2- concentrations over the HSO4 minus concentration, which is 0.1 plus X times X over 0.1 minus X, and that equals the looked up value, K sub A2, 1.2 times 10 to the minus 2. So this is the equation we're going to have to solve for X. There we go. There it is, with a little room to show the results. Set this up, solve for X. We get X equals 0.0098. And then the other thing to be aware of is, unlike in the monoprotic acid calculations, this X does not represent the H3O plus concentration. Because we've had two dissociations, and the first dissociation gave 0.1 molar H3O plus, and then the second dissociation adds another 0.0098. So, to do our calculations and to get the pH, we need to add up the 0.1 and the 0.098 molar H3O plus concentrations from the two dissociations. This works out to be 0.11 molar overall, so we didn't get too much from the second dissociation, we got a little bit. And then the H3O plus concentration, if we take the negative log of that, that gives us the pH, and that worked out to be 0.96 for 0.1 molar sulfuric acid H2SO4 solution. The same process is used for triprotic acid calculation, except we'd have a third dissociation. And then, of course, the reminder is most diprotic acid calculations, the first dissociation won't be complete like it was for the H2SO4. So you'd actually be solving an equation for X for the first dissociation and then plugging those values in, so you'd have two calculations to do. And that is it for the rest of the material from the Wednesday class, or what we would have been missing on Monday. Hope you have a great 4-day weekend. See you on Wednesday the 22nd in class.